study about the binary adder subtractor and then magnitude comparators. So adder, the most basic operation is the addition of two binary bits. The combinational circuit which perform the addition of two binary digits are called as adders. So the simple addition of binary bits consists of four possible elementary operations such as 0 plus 0, 0 plus 1, 1 plus 0 and 1 plus 1. So the results of this addition gives 0 plus 0 is equal to 0, 0 and 1 added together to give 1, 1 plus 0 give 1, 1 plus 1 we have 10 here. So the first three operation produce a sum whose length is one digit, but when the last operation is done, the sum is two digits. So the higher significant bit of this result is called as carry and the lower significant bit is called as the sum. The logic circuit which performs this addition operation is called as half adder. The addition of two bits, if the logic circuit performs the addition of two bits, it is called as a half adder. If the circuit performs the addition of three bits, it is called as a full adder. So here is the question. Design a half adder and full adder. We need to design the half and full adder using the logic gates. So the two binary bits are called as AND and add-in bits. So the two binary inputs are called as the AND and add-in bits, and two binary outputs are called as sum and carry. So the first one is the truth table for half adder. So half adder denote the addition of two bits, addition of two binary bits. So here the inputs are defined as A and B. So the possible combinations are provided and the outputs here are the carry and sum. When we add 0 and 0, the carry is 0 and sum is also 0. When you add 0 plus 1, sum is 1 and carry is 0. 1 plus 0, sum is 1 and carry is 0. 1 plus 1, the sum is actually 1 plus 1 is 10. So the 10 is written as carry 1 and sum 0. So the block diagram of half adder include two inputs and two outputs, two inputs A and B and two outputs sum and carry. Sum is denoted as S and carry is denoted as C. So using this truth table, you need to derive the expression for the carry and the sum output. So the derivation of expression is done by using the K-map simplification. So separate K-maps were drawn for sum as well as for carry. So since it involves only two variables, so we can draw two variable K-map. So in a two variable K-map, there are totally 4 cells. So and two variables A and B. So these 4 cells are filled up in the order of the given output. So carry is filled as 0, 0, 0, 1 and sum K-map is filled as 0, 1, 1, 0. And then grouping is done. So grouping is done by single ones. So pairing cannot be done here in this case. So carry will result in the expression AB and sum will result in the expression AB bar plus A bar B, which can be shortly written as A XOR B. So using these equations, we can draw the logic diagram, which gives the logic diagram of a half adder. So we have two inputs A and B. When you XOR these two inputs, you get the sum of the expression, and when you multiply these two inputs, you will get the carry of the expression. The next one is the full adder. Full adder is a combinational circuit that forms the arithmetic sum of 3 bits. Full adder is a combinational circuit that performs the arithmetic sum of 3 bits. So it consists of 3 input and 2 outputs. Two of the input variables are denoted by A and B, and third input is denoted by C in. So the C in represent the carry from the previous LSB, and the two outputs are denoted as sum and carry. So the block diagram of full adder is shown in the figure. Coming to the truth table of full adder, we have three inputs A, B and C in, and two output C out, that is carry and sum. So we have to perform the addition of 3 bits, which is almost similar to the half adder. Only one difference is that addition of 3 ones, that is 1 plus 1 plus 1 gives 11. So that the sum is 1 and carry is 1. Only that is the difference here. So according to the outputs received in the carry and the sum, we need to draw the K-map for separately for carry as well as for sum. So when you enter the elements, the grouping can be done in pairs. For carry, grouping can be done in pairs. For sum, grouping cannot be done. Therefore, separate ones are taken and the corresponding expressions will have to be written. Then further simplification of the sum expression can be done, and finally we can arrive at the expression C in XOR A XOR B. So use for this expression, the logic diagram is drawn. Also, this full adder can be drawn using two half adders. So when we go to simplify further expression in carry, so we will arrive at the expression AB plus C in A into A XOR B, and the sum is C in XOR A XOR B. So using this expression, we can derive the full adder using two half adders. So the diagram is shown here. Subtractors. The subtractors will perform the function of subtraction. So here we will not have the sum and carry. Instead of sum and carry, we will have the difference and borrow. So here also we have two types, half subtractor and full subtractor. Half subtractor will perform the subtraction of 2 bits, and the full subtractor will perform the subtraction of 3 bits. So the truth table of half subtractor is shown. So 0 minus 0, difference is 0 and borrow is 0. 0 minus 1, we have to borrow 1, so that we can make the 0 as 10. So that 10 minus 1 will result in 1. So that difference is 1 and borrow is 1. The next one is 1 minus 0. The difference is 1 and borrow is 0. 1 minus 1, difference is 0 and borrow is 0. So as usual, except for 0 minus 1, the remaining terms will be subtracted as usual. So we got the outputs for difference and borrow. So these zeros and ones have to be filled up in the K-map for simplification and arriving at the Boolean expression. So two different K-maps were drawn for the difference as well as for borrow. So borrow expression A bar B and difference expression is A XOR B. So for these two equations, we can draw the logic diagram. Next comes the full subtractor. Full subtractor is a combinational circuit which performs the function of subtracting 3 bits. So the 3 inputs are used here, A, B and B in. B in is the borrow in, and the outputs are difference and borrow out. So we need to subtract 3 bits and write the difference and borrow. So using these elements, we have to do the K-map simplification and arrive the difference and borrow equations. So using these equations, we can further simplify the difference equation using XOR gate. So using these expressions, we can draw the logic diagram of a full subtractor. So like full adder, full subtractor can also be constructed using two half subtractors. So further we need to do some manipulations in the borrow out equation so that we can arrive at the final simplified expression which we can use it for half subtractor. The next one is a magnitude comparator. So this magnitude comparator will compare the magnitude of the bits received. Okay, so it receives two n-bit numbers A and B as inputs, and the outputs are the comparison of the inputs. The comparison involves three cases: greater than, less than, and equal to. So which case is true, that case will become high, and the remaining cases will become low. So this is an example of one-bit comparator using basic gates. So when coming to the one-bit comparator, we have only one bit in A and one bit in B. So A and B are the inputs, and the outputs usually have three cases: A equal to B, greater than B, A less than B. Whichever case is true, that will be high, and the remaining case will be low. So for example, the first row, A is equal to 0, B is equal to 0. As both A and B are equal, the first case A equal to B is satisfied. So only in that case, one is remains high. The remaining two cases, it becomes low. The output become low. Similarly, if A equal to 1 and B equal to 0, which case is true means A greater than B is true. So only for that case, the output remains high, and for the remaining case, the output remains low. So similarly, we need to find out the comparison. We have to compare the magnitude for all the possible combinations, and we have to derive the outputs. So finally, we need to draw the K-map expression for all the outputs. So from that, we can get the simplified expression of each and every output. For example, if y equal to b means the expression is a x nor of b. For y a less than b, the expression is a bar b. For y a greater than b, the expression is a b bar. So using this a and b, we can draw the expression using logic gates, and finally we can get the logic diagram of the one-bit comparator. Similarly, this is for design of 2-bit comparator. So in 2-bit comparator, each variable, that is A variable, has 2 bits and B variable has 2 bits. So these 2 bits and 2 bits are compared, and the outputs are determined for which case is true. The remaining outputs are determined as 0. So accordingly, we have 16 possible combinations. So for all the 16 possible combinations, the magnitude is compared and the output is written. So next we have 3 outputs. So we need to draw the K-map for 3 different outputs. So using 4 variable K-map, we need to draw the outputs of K-map, and we need to do the grouping. So as per the grouping, we will arrive at some simplified expression. So using those expression, we can draw the logic diagram of a magnitude 2-bit magnitude comparator. Thank you.